This lecture is the continuation of my earlier lectures on basic quantum mechanics. In my last lecture, we discussed about the classical and quantum harmonic oscillator. We talked about the position and momentum operators x and p for the quantum oscillator. Using the Heisenberg equation of motion, we obtained the time evolution of the position and momentum operators as xt is equal to x0 cosine omega t plus p0 by m omega sine omega t, and the momentum operator pt is equal to p0 cosine omega t minus m omega x0 sine omega t. And one can easily check that these two operators, the commutator between these two operators x and p at any given time. So one can calculate the commutator between the operator xt and pt, which is xp minus px, that is equal to x0 comma p0. This commutator is equal to IH bar identity. That means the commutator, the value of this commutator at any given time is reserved. The value of this commutator at time t is equal to the value of the commutator at time t equal to 0, which is IH bar times the identity operator. And one can also check that the Hamiltonian operator, which is p square by 2m, p at any given time plus half m omega square xt square. If one calculate this Hamiltonian at any given time using this time evolution operators, this is p hat t square, that means p hat t times p hat t, and this is x hat t square, means x, it is equal to x hat t multiplied by x hat t. So if one substitute these expressions of pt and xt from here, one can easily check that this is equal to p0 square by twice m plus half m omega square x hat 0 square. That means the Hamiltonian at any given time has the same form. This is the Hamiltonian at time t equal to 0, this is the Hamiltonian at time t equal at any given time. And so this was the dynamical picture of this problem. Today in this lecture I will discuss about the quantum states, not just the observables, but here we will talk about the quantum state of the system, that is the harmonic oscillator here, and specifically the energy eigenstates of the quantum harmonic oscillators. When we talk about quantum state and its time evolution, the equation that immediately comes to our mind is the Schrodinger equation. Okay, so from my earlier lecture on Schrodinger wave equation, we know that Schrodinger equation for a quantum particle moving in a potential Vx, a quantum particle moving in a potential Vx, can be written in the position representation as follows. So this is the Schrodinger equation. If we remember, is I h bar time derivative del t psi x comma t is equal to h psi xt, where this psi xt is called the wave function. This is called wave function representing the state at a given time, and this h is the Hamiltonian. H is the Hamiltonian, which is equal to minus h bar square by twice m del square by del x square plus the potential of the potential energy. So this is the kinetic energy part, this is the potential energy part of the Hamiltonian. And we also said that usually it is difficult to directly solve this time dependent Schrodinger equation. So it is usually very difficult to solve directly this time dependent Schrodinger equation. For that, what we do, we first solve the eigenvalue equation for the Hamiltonian. So we first solve the eigenvalue equation for this Hamiltonian operator to obtain the energy eigenstates, and once we have the eigenstates and the eigenvalues of the Hamiltonian, it is relatively easy to calculate the time evolution of any arbitrary initial state of the system. So here for this quantum harmonic oscillator problem, the potential, as we know that this potential has this parabolic form. This is the potential, right, x. In my previous lecture we have seen that this harmonic oscillator potential was half m omega square x square. So this represents a parabola. So I substitute the expression over here. So then we have the Hamiltonian for this harmonic oscillator becomes this h bar squared by twice m del square by del x square plus this potential energy, potential term half m omega square x square. So this represents the kinetic energy part, this is the potential energy part, and this actually we obtained from that expression because we remember that the Hamiltonian for harmonic oscillator was, we wrote in this way, right, the p square by twice m plus half m omega square x square. So basically if we know that the momentum operator in the position representation, we can write this as minus I h bar del by del x. This is the operator for the momentum in position representation. So if we substitute this expression of this momentum operator over here, we will directly get this operator. So that is the kinetic, this is the kinetic energy part and this is the potential. So from here actually p square we will get this double derivative del square by del x square. So this is the Hamiltonian. So this is the Hamiltonian for this harmonic oscillator problem. So first we solve the eigenvalue equation for this Hamiltonian operator. So first we solve the eigenvalue equation for this Hamiltonian. So this is the Hamiltonian for a particle in a harmonic oscillator potential. Here first we solve the eigenvalue equation for this Hamiltonian, which is, so we first solve this eigenvalue equation, h psi nx is equal to En psi nx. So this is the eigenvalue equation for the Hamiltonian, where this En, these are the eigenvalues of the Hamiltonian, and psi nx, they are the eigenstates of the Hamiltonian. So let us now substitute this expression over here, then what we will obtain. So if we substitute this expression of h over here, we will obtain this equation, minus h bar square by twice m del square psi nx by del x square plus half m omega square x square psi nx are the eigenstates. This is equal to En, yeah, h acting on psi nx, that part gives me, the left hand side gives me this, right hand side is En, the eigenvalues times the eigenstates psi nx. So this is also called the time independent Schrodinger equation for this harmonic oscillator problem. So this is called the time independent Schrodinger equation, and the solution for this equation can be obtained in terms of the Hermite polynomial. The solution for this equation can be obtained in terms of the Hermite polynomials. So the solutions are psi nx has this form, this is equal to m omega by pi h bar to the power 1 by 4 1 by 2 to the power n factorial n square root of that. The Hermite polynomials hn, the argument is square root of m omega by h bar x, and then there is an exponential factor over here, e to the power minus m omega divided by twice h bar x square. So these are the solutions for this equation, that is the energy eigenfunctions or the energy eigenstates for the harmonic oscillators, where we see that these are the Hermite polynomials, which are the solutions for a Hermite differential equation. These are the eigenstates for the harmonic oscillator, which will satisfy this eigenvalue equation for the Hamiltonian. And here we note that these are actually the Hermite polynomials. For n equal to 0, this polynomial has this form, that will be h0, in the argument it is something times x. So h0 whatever in the argument, then it will become 1, and for this is for n equal to 0. For n equal to 1, similarly these Hermite polynomials have different expressions, which I am writing over here. So this is m omega by h bar x, this is equal to 2 times 2 multiplied by this argument m omega by square root of m omega by h cross x, and h2 similarly we can go from n equal to 0 to n equal to infinity in principle. And the ground state is, so n equal to 0 is the ground state of this harmonic oscillator, which is, so if we put n equal to 0 over here, that will give us the ground state for this harmonic oscillator. So let us write that ground state of the harmonic oscillator, which is psi 0 x. So the ground state or the lowest energy state for this eigenvalue problem. So that will be psi 0 x. So here from here we have m omega by pi h bar to the power 1 by 4. N is equal to 0 means 2 to the power 0, that is 1, 0 factorial is 1. So this factor becomes 1. H0 in the whatever in the is there in the argument, that will give me 1. So this factor also becomes 1. Then we have only this factor left, e to the power minus m omega by twice h bar x square. So this is a Gaussian function, we can easily see that. So this represents the ground state of the harmonic oscillator in the position representation. Okay, we can construct all the higher energy excited, all the excited states for the harmonic oscillator using that creation and annihilation operator that I will show you in my next lecture. And similarly, we will have the other excited states. We can put n equal to 1, n equal to 2 like that. So we can also obtain all the higher energy excited states, psi 1x, psi 1x, psi 2x and psi n, similarly psi nx. And this is the eigenstate of the Hamiltonian. The eigenvalues of the Hamiltonian are also, this is the eigenstate of the Hamiltonian. The eigenvalues for the Hamiltonian can also be obtained. Actually, where the eigenvalues of the Hamiltonian are given by this eigenvalues of the Hamiltonian En for this harmonic oscillator problem, one can easily derive. For this part, I will suggest you to follow any standard textbook of quantum mechanics. So the eigenvalues for this harmonic oscillator problem is given by this. En is equal to h bar omega n plus half. These are the eigenvalues for this harmonic oscillator problem. For example, the ground state energy or the eigen energy, ground state eigen energy E0. So we will have to put n equal to 0 here. So that will be h bar omega by 2. So we can write it that half h bar omega. The next energy level is E1. The energy eigenvalue E1 is equal to n equal to, if we have to put n equal to 1 plus half is 3 by 2. So that will be 3 by 2 h bar omega. So similarly, we will have all the energy eigenvalues from this equation. We can put n equal to 2 next and then so on. And the separation between the energy levels, that means these energy levels are equidistant. That means E1 minus E0 will be equal to E2 minus E1. So these energies for the harmonic oscillator problem, the energy levels are equidistant. The energy levels are equidistant for this harmonic oscillator problem. And one can actually one can also show a few eigenfunction for this problem, that is psi 0, psi 0x, psi 1x, psi 2x. So I can show you how they actually look like. So here I am showing a few plots of this energy eigenstates, psi 0x, psi 1x, psi 2x. Here we can actually draw these functions, how they look like. I just wanted to show you a few plots here. This is my x axis. So if this is the energy axis, so you can imagine maybe this is the potential harmonic oscillator potential, and the energy levels are equidistant. So something like this. This I can say that this is my E0, that is half h bar omega, and the next energy level, so they are equidistant actually. So this is my first excited state, E1 is 3 by 2 h bar omega. The next energy level is E2. So similarly, we will have all the higher energy states. So this is the ground state, first excited state, second excited state, like that, and the eigenfunction corresponding to those energy eigenvalues are this. I am trying to draw actually here the functions, that is so I just little bit extend the axis over here. So they will look like this. This is the ground state wave function psi 0x. It looks like a bell shaped function, that is a Gaussian function, and for corresponding to this energy eigenvalue, the eigenstate looks like this. psi 1x, the energy eigenstate, next energy eigenstate corresponding to this eigenvalue. Psi 1x looks like this, and then we have the next energy eigenstate corresponding to this eigenvalue, which looks like, and the next energy eigenstate corresponding to this eigenvalue will look like this, which is psi 2x actually. So psi 2, this is my energy eigenstate corresponding to this energy eigenvalue E2 is 5 by 2 h bar omega. So the energy eigenstates for this harmonic oscillator, a few energy eigenfunction I have shown over here, and these are the energy eigenvalues for this harmonic oscillator. Energy eigenstates of the harmonic oscillator or the eigenstates of the Hamiltonian for the harmonic oscillator are given by these functions, and these eigenfunctions or the energy eigenstates, all the excited energy eigenstates, they can be also constructed using a very nice technique. We can actually express our Hamiltonian for the harmonic oscillator in terms of the creation and annihilation operators. So two very useful operators for this problem, the creation and annihilation operators. We will use the position and momentum operator. Position and momentum operator we have discussed in our previous lecture. So using those operators, that is the position and momentum operators, we can construct two very important operators for the harmonic oscillator, namely the creation and annihilation operators as follows. So for this problem of harmonic oscillator, we can construct these operators. A is called the annihilation operator, which is combination of position and momentum in this way. So this is m omega by square root of m omega by 2h bar x is the position operator, plus I is the imaginary, and 1 by twice m omega h bar square root of that the momentum operator, and its Hermitian conjugate, that is a dagger, which is called the creation operator. Why they are called creation and annihilation operator, we will see it later. So a dagger can also be constructed. We can construct this operator also using this position and momentum in this way: m omega by twice h bar square root of this x minus the imaginary I, and 1 by twice m omega h bar square root of that, and then p. So these are called creation and annihilation operators, and we can actually invert the equation to get the position and momentum operator also in terms of these operators a and a dagger. So if we invert the equation, then we will obtain this position and momentum operator in terms of the a and a dagger. X, the position operator, will be h bar by twice m omega square root of that multiplied by a plus a dagger. So I am not writing everywhere, so please keep it in mind, they are operators. So I should put a hat here, a plus a dagger, and p, the momentum operator, can also be expressed in terms of this a and a dagger in this way: minus I m omega h bar by 2 square root of m omega h bar by 2 a minus a dagger. The position operator is proportional to this a plus a dagger, and the momentum operator is proportional to a minus a dagger. So these are the some prefactors are there, the constant prefactors or C numbers are there, and using this creation and annihilation operator, we can express the Hamiltonian of the quantum harmonic oscillator also. Let us see how can we express the Hamiltonian of the quantum harmonic oscillator in terms of a and a dagger. So these are creation and annihilation operators expressed in terms of position and momentum operator. So it is important to point out that these two operators, they are not Hermitian, that is a dagger is not equal to a, but using this non-Hermitian operator, we can construct Hermitian operator like position and momentum, which can be expressed in terms of a and a dagger. Similarly, the Hamiltonian can also, Hamiltonian we know that it is a Hermitian operator, so that can also be expressed in terms of the combination, in terms of these operators a and a dagger. So it is important to note that these two operators, the a and a dagger, they are actually not Hermitian operators. So if you take a dagger, that is not equal to a, but the position and momentum operator, they are Hermitian because they are physical observables, and we saw also, we have also seen that this position and momentum operator, they can be expressed in terms of a and a dagger. So x was proportional to a plus a dagger, and p, the momentum operator, we have seen that can be expressed as a minus a dagger, means they are proportional, there are some constant prefactor over there. So even if the operator A and A dagger are non-Hermitian, that is they are not Hermitian operator, but their combination we can actually use these operators to construct Hermitian operator like position, momentum, they are physical observables, and also we can construct the Hamiltonian using these operators. Means the Hamiltonian can be expressed in terms of this creation and annihilation operator, and exactly that is what we are going to show over here. So let us now calculate this operator A dagger A. Okay, A dagger A. So that is equal to, what is A dagger? So that operator m omega by twice h bar x minus I 1 by twice m omega h bar p. So this is A dagger. Then we have A is then this one m omega, sorry, there is a square root over here, square root of 2 m omega by twice h bar x plus I, the imaginary I 1 by twice m omega h bar p. So this is my the A operator. So this is A dagger and this is A. So we have to multiply these operators. So if we multiply, okay, let us multiply one by one. This multiplied by this will give me, so this will give us m omega by twice h bar, square root of that, and the same thing square root of m omega by twice h bar, that will give us m omega by twice h bar, then x into x means x square basically, and then this multiplied by this, so that will give us I, this factor, constant factor, and square root of m omega by twice h bar, then xp, right, xp. Okay, the next term will be minus I, this with this, so that will be minus I square root of 1 by twice m omega h bar, and the constant factor is there, square root of m omega by twice h bar, and px. So here it is px, and the last term will be this multiplied by this, so I am writing it over here. I into I will give I square, so that is minus 1. So this multiplied by this will be, there is a minus sign over here, so it will be plus actually. I into I minus 1, and minus is there, so plus 1, and these two factors if I multiply, it will give us 1 by twice m omega h bar, 1 by twice m omega h bar, p into p, that is p square, p into p. Next we focus on these two terms. Let us now focus on these two terms, that is this xp, and please remember that xp is not equal to px. In quantum mechanics, x and p, they don't commute, so we have to take care of that. Now here, from here we can see this omega will cancel with this omega, this m will cancel with this m. So from here we will get, so this term will be I, and then 2 h bar, this is 2 into 2 h bar into h bar, so 1 by 2 h bar. So this will be I by twice h bar xp, and from here we will get minus I, this will give us minus I, the same factor I think, because m cancels, omega cancels, so we will have 1 by 2 I by, I can write it as I by twice h bar, then px. So I am now focusing on these two terms only. So here we can see that I can take common this constant factor. So this I by 2 h bar, I can take this factor I by twice h bar as common. So then I will have xp minus px, and we know that this is actually the commutator between these two operators x and p. So this is equal to I by twice h bar x comma p, the commutator, and we know that the commutator x comma p, that is equal to I h bar. If you want, you can put an identity. So this is exactly equal to I by twice h bar multiplied by this commutator. The value of this commutator is I h bar, so I put it here, I h bar. So this is equal to I by twice h bar, and this is the commutator x comma p, and the value of this commutator is ih bar identity. So I substitute the value of this commutator over here. Then finally we will have this h bar and h bar cancels. So I into I is -1. So this term gives us minus half identity. So these two terms together gives us this thing, minus half actually. And now we focus on this term and this term. So then we write down the resultant equation. That means what a dagger a finally we have is m omega by twice h bar x square 1 by plus 1 by twice m omega h bar p square plus these two terms, which together gives us minus half. Okay, so that let us write it clearly here. So finally we have the expression for a dagger a is equal to m omega by twice h bar x into x plus 1 by twice m omega h bar p into p minus half identity. I am not explicitly writing the identity operator, but it is implicit that there is an identity multiplied by half. So now this can be expressed as, so this is equal to m omega by twice h bar x square plus 1 by twice m omega h bar p square minus half. So if I take half, if I bring this minus half factor in the left hand side, what we will get, this a dagger a plus half, that will be these two terms, that will be given by, this is equal to m omega by twice h bar x square plus this 1 by twice m omega h bar p square. Okay, now what we will do, now we will multiply the left hand side and right hand side by a factor of h bar omega. So let us multiply both sides by h bar omega. So the left hand side will be a dagger a plus half multiplied by h bar omega. So this side will be h bar omega. I am multiplying both sides by h bar omega twice h bar x square plus h bar omega, and this factor 1 by twice m omega h bar p square. So now here we can see that this h bar will cancel with this h bar, and here this h bar will cancel with this, omega will cancel with this. So finally from this equation what we have is h bar omega a dagger a plus half, that is equal to, on the right hand side we have half m omega square x square plus here p square, in the denominator there is factor of twice m, so this is p square by twice m. So we see that on the right hand side this is exactly the Hamiltonian for the harmonic oscillator, which is equal to h bar omega a dagger a plus half. So now we expressed our Hamiltonian. This is the Hamiltonian for the harmonic oscillator. The Hamiltonian for the harmonic oscillator can be expressed in terms of this a and a dagger, the creation and annihilation operators. So the Hamiltonian of the harmonic oscillator square by twice m plus half m omega square x square. This Hamiltonian, we could express this Hamiltonian in terms of this a and a dagger, the creation and annihilation operator, in this way, a dagger a. So both are same actually. So now expressing the Hamiltonian in this way actually give us dividend. Expressing the Hamiltonian in terms of this creation and annihilation operator is very useful. Now we can easily see that this Hamiltonian is certainly the Hermitian operator, and we will also see that this a dagger a, this combination, I mean individually even if they are not Hermitian, this a dagger a is Hermitian, and this operator is called the number operator. So a dagger a, this operator is called number operator. So this operator is called the number operator, which is Hermitian. So here I can write this as h bar omega number operator plus this half, right. So once we expressed the Hamiltonian in terms of this number operator, or in terms of this a dagger and a creation and annihilation operator, we can write down the eigenvalue equation for the Hamiltonian also. The eigenvalue equation for the Hamiltonian, we can write it as, the eigenvalue equation for this number operator is this. So this is the number operator. Its eigenstates are this ket n, ket vector n. So n acting on the eigenstates of this number operator gives us the eigenvalues. The eigenvalue equation for this number operator is I have written the eigenvalue equation for the number operator n here. So this is the number operator, and we can write down the eigenvalue equation for this number operator in this way. So this is the eigenvalue equation for the number operator. The number operator acting on the ket n are the eigenstates for this number operator, which will give us n times n. So these are the eigenvalues, small n. So these are the eigenvalues. This is the eigenstate for this number operator. So this is the eigenvalue equation for this number operator. Now let us come back to the Hamiltonian for this harmonic oscillator, which is expressed in terms of this number operator. So this Hamiltonian is equal to h bar omega n plus h bar omega by 2. There is an identity operator over here. Now we will see that the eigenstates for this number operator are also the eigenstates for the Hamiltonian, because if we apply this Hamiltonian on these eigenstates for the number operator, what we will get? So h acting on the eigenstates, these number eigenstates n, that will give us on the right hand side we have this, right, h bar omega n acting on the number eigenstate n plus h bar omega by 2. This ket n is there, this is identity, so this will be ket n. Ket n multiplied by the identity will give us the same vector. So h Hamiltonian acting on this number eigenstate gives us this. So this is equal to h bar omega n is the number operator acting on n, gives us the eigenvalue times the state again. So this will give us this small n, these are the eigenvalues, times the number state n plus h bar omega by 2 n. So this we can write, we can take again h bar omega as common, and h bar omega n is just a number here because it is eigenvalue, it is a real quantity, eigenvalue of a Hermitian operator. So this n, this small n are numbers, some numbers. So this will be n plus half n, right, because on the right hand side there is this state again. So what we obtained, the Hamiltonian acting on this state gives us some eigenvalue times the state again. That means these are eigenstates for the Hamiltonian also with these eigenvalue. So what we obtained, so until now what we have done, we have expressed the Hamiltonian in terms of the creation and annihilation operator, or in other words this number operator, and then we saw that the eigenvalue equation for the Hamiltonian can be expressed in this way, where the Hamiltonian acting on these states gives us the eigenvalue. So these are the eigenvalues for the Hamiltonian, that is the energy eigenvalues, right. So these are the eigenvalues for the Hamiltonian. En is equal to h bar omega n plus half, and these are the eigenstates for the Hamiltonian, this ket n, they are the, so you can say that these are the eigenstates for the energy eigenstates for the Hamiltonian. So h acting on these energy eigenstates gives us these eigenvalues, energy eigenvalues, which are h bar omega n plus half times the energy eigenstate again, and using this we can have all the energy eigenstates, we can obtain all the energy eigenstates that I will show you in my next lecture. And so basically we have various energy levels for the harmonic oscillator, the energy eigenstates which I told you already. For example, this for n equal to 0, for n is equal to 0, this is the ground state, and the ground state energy will be given from here. So the ground state energy E0 is equal to h bar omega half h bar omega, and the next energy eigenstate n is equal to, the next energy eigenstate will be given by n equal to 1, and that is E1, the energy eigenvalue will be 1 plus half 3 by 2 h bar omega. So similarly all the energy eigenvalues we can obtain from here. The energy eigenvalues for the Hamiltonian, are given by this. En is equal to h bar omega n plus half, where n is equal to 0, 1, 2, 3, etc. So there can be infinite number of energy levels in principle for the harmonic oscillator. We have to put n is equal to 0, 1, 2, 3 like that, and we will get all the energy eigenvalues or energy eigenstate. Now these energy eigenstate corresponding to this n equal to 0, there will be the energy eigenstates also. So those energy eigenstates I am writing over here. So corresponding to this energy eigenvalue, there will be this energy eigenstates n. So in short, we are writing this n is equal to 0. This means ket 0. Corresponding to this eigenvalue, we will have the next energy eigenstate ket 1. So similarly, E2 will be 5 by 2. This is the eigenvalue, and there will be an energy eigenstate ket 2. So here these energy eigenstates are in abstract ket space, right? 0, 1, 2, ket 0, ket 1, ket 2. We have not expressed them in the position representation. So in next lecture, I will show you how we can express them in the position representation also. And there is another point here, that these energy eigenstates, that means this the energy eigenstates which I already have discussed this in terms of that Hermite polynomials. Those energy eigenstates are basically, they are the same. Here I have expressed in abstract ket space. So if you express them in the position representation, they can be expressed in terms of a function. We call it wave function, which I wrote in terms of Hermite polynomials. So those functions represents the energy eigenstates. So in position representation, they look like this. I have already shown you how these energy eigenstates actually looks like in the position space. But the point is that here this abstract 0, 1, 2, they are the same energy eigenstates, but here I have not expressed them in the position representation, and we can easily do that. Relatively, it is easy to work in this ket space for the Hamiltonian, and we can obtain all the energy eigenstates very easily using this creation and annihilation operators. So operationally, this is very nice technique to obtain all these energy eigenstates 0, 1, 2, even if here I have not expressed them in the position representation. So that is what I will do. That is what I will do in my next class. So how to express this abstract ket 1, ket 2 in the position representation. Please keep it in mind that whether I am writing the eigenvalue equation of the Hamiltonian in this abstract ket space, or we are solving the time independent Schrodinger equation from the beginning, if we start solving the equation in the position representation, then also we can get the same eigenstates for the Hamiltonian. But the another technique is this one, where I have not actually gone to the position representation. I am working in the ket space of the Hamiltonian, some abstract Hilbert space. So here also this Dirac Ket notation, these states are written in Dirac Ket notation. These energy eigenstates are written, and these two are actually the same thing, but one in abstract Ket space, Dirac Ket space, we have expressed the energy eigenstates. Another one from the beginning, if we start in to solve the equation in the position representation, then also it is fine. You can obtain the energy eigenstates in terms of the Hermite polynomial. So in next class we will see that how to express those these Ket states, all these things in the position representation. So the last point I want to make here is that for quantum systems, so because this system is quantum, right? So quantum systems, these energy eigenstates are not the only states for the system. So these energy eigenstates, this ket 0, ket 1, ket 2, ket 3, they are not the only allowed quantum state for the system. We can have, for quantum systems, we can actually prepare a state which can be in a superposition of for example 0 and 1. So there can be states that we can prepare which are in the superposition of various eigenstates of the Hamiltonian. So that also is a very important point. That is also a very important point, because quantum systems we can prepare superposition states out of these eigenstates. There can be states which are in the superposition of these energy eigenstates. So for example, we can have a state like this. So this is the ground state of the harmonic oscillator. So 1 by root 3, I can prepare some state in a superposition of ground state 0, 1 by root 6, 1 plus 1 by root 2, 2. So this is a quantum state which is in a superposition of 0, 1 and 2. So 1 by root 3, 0, Ket 0 plus 1 by root 6, Ket 1 plus 1 by root 2, Ket 2. And these coefficients, they represent the probability amplitude. So if we do the square modulus of this thing, that means square of this thing is 1 by 3 plus 1 by 6 plus 1 by 2. So this will give us 1. Okay. So total probability should be 1. So normalized state. But this type of states are now routinely prepared in a laboratory. So this we have to keep it in our mind, that this is a quantum system. Here we are talking about this harmonic oscillator is quantum. So hence we can have such kind of strange states also, which can be in a superposition of all these various energy eigenstates like 0, 1 and 2. Thanks for watching. Please don't forget to subscribe the channel and tap the bell icon to get notified for my new lecture videos. Please comment below. Your thoughts and suggestions would be greatly appreciated.